Welcome to this QUPES how-to video where we illustrate how to analyze a frequency selective surface, an FSS, using QUPES at antenna level. We continue from the previous video where we optimized an FSS unit cell geometry to reflect in Ka band between 20 to 24 GHz and be transparent in the S band between 2 and 2.3 GHz. If you're interested in how to design the FSS unit cell, check the previous video. In the present video, we teach you how to apply the optimized FSS periodic unit cell on an actual antenna surface. To this end, we'll consider a simple dual reflector system. This requires the use of grasp, as reflectors and curved surfaces are needed. To set up the reflector system, we use the grasp wizard at Ka band. We click on Wizard, Grasp Wizards, Ring Focus Reflectors. We want to consider a Cassegrain system, so we set this frequency to 22 GHz, which is the center frequency of the Ka band, and we proceed using the default settings. The wizard generates all the objects that are needed to carry out the analysis of this reflector antenna system: the reflector objects, the rim and surface objects, the physical optics analysis objects, the feed, and various convenient coordinate systems. Some of these objects will also be used for the definition of the Fss Sub Reflector. To create the Fss Sub Reflector, we create a new periodic surface object. We select the periodic unit cell object defined for Ka band. For the coordinate system, rim and surface, we select those that describe the subreflector. The FSS is now shown in the 3D plot, and to better see the FSS, we remove the original subreflector from the view. We can now see the FSS substrate consisting of the two-layer loops. For the analysis, we create a periodic MOM object using the dedicated method for layered media. We set the frequency and scatter references and proceed with the default settings for the rest. In the Command tab, we can see the new commands generated by the Grasp wizard and the previous commands which we will deactivate. Then we need to modify the analysis sequence such that we analyze the FSS subreflector instead of the solid metallic subreflector. To this end, we change the first get currents command such that the target is our periodic MOM object, and we deactivate autoconvergence because this is a feature only available for physical optics analysis. We change the second get currents commands to use our periodic MOM object as source. The add field command is modified to include the contribution from the FSS subreflector and not those from the metallic subreflector. We now execute these commands. The analysis takes approximately 30 seconds, and we can go to the Results tab to see the far field pattern. It shows a peak gain of 45.6 dBi from the antenna, indicating that the FSS correctly reflects the feed pattern onto the main reflector. To carry out the S-band analysis, the user needs to define the S-band feed in the proper position and simply repeat the analysis for this frequency. Thank you for watching this QUPES how-to video on how to optimize an FSS and on how to analyze it at the antenna level. We hope you found it useful.